Hello everyone, welcome to another video. Today you will learn how to apply polynomial regression using Python's Scikit-Learn library. As usual, I prepare a notebook to do this video and I will share a link to this notebook in the video description. I will also share a link to the data file that I will use in the video. All right, I'm going to use Python using Google Colab. So as you can see, I prepare a Python notebook with Colab. Okay, and this is the notebook that I will share with you. All right, let's go ahead and start. First, we import all the functions and libraries that we need for applying polynomial regression. Okay, let's go ahead and do that. That will be this first code cell. Then let's go ahead and retrieve the data. The data I will use for this video is the auto data set. This is a well-known data set in the machine learning community. It's a data set with data about 392 different car types and models. And the goal with this data set is to predict the car's miles per gallon. So the target variable to predict here is the miles per gallon. Okay. I have a CSV file with this data set stored locally right here. And what I'm going to do is I'm going to upload that file to Colab, all right? And to that, what I'm going to do is I'm going to open the Files tab right here on the left. That's the Files tab. I'm going to open it, and I'm going to drag and drop the CSV file with the data to that Files tab. Okay, drag and drop it right here, okay? You drop it right there, you get this warning saying like, hey, once you close the Google Colab notebook, the file is going to disappear. That's okay. That's fine. We can use the file as long as we have this notebook open. That's fine. Okay, so you can click OK. That's good. After you have the file in Colab, what you need to do is you need to copy the path to that file because our goal is to be able to read this CSV file into a data frame, into a pandas data frame. And to be able to do that, we need the path to that file, okay? And so to get a path to this file, you're going to click these three dots, then you're going to click copy path, okay? Perfect. Once you do that, you can go ahead and close the Files tab. And then this is what you're going to do. You need to create a variable to store that path, okay? And I did that right here. Let me delete it and kind of start over, okay? So you need to have a variable with to store the path, okay? So in this case, I created a variable titled path auto data, and I'm going to store the path right there. So I'm going to say that equals, and then I'm going to do Control V, paste the path. That's the path that we copied, okay? And then what you need to make sure is that you enclose the path in quotes. Okay, don't forget that. Enclose the path in quotes, and that's fine. That's your variable with the path. Now, what you're going to do is you're going to use that path as the argument to the read underscore CSV function in pandas, and that will read the CSV file into a data frame. Okay. Let's go ahead and execute this code cell. And now we have a data frame, AutoDF, which is the data that we're going to use in this video. Okay, let's take a look at that data frame. We have, as I said, data for 392 observations or cars. And for each car, we have data about the miles per gallon. And again, this is the target that we want to predict, miles per gallon, the number of cylinders, the engine displacement, the horsepower, and so on and so forth. Okay. Perfect. The first thing I'm going to do before actually applying polynomial regression is I'm going to delete two columns that I'm not going to consider as predictors, and they are the name of the car and origin. The name of the car is just the name of the car, like Toyota Corolla, Honda Civic. That's kind of useless as a predictor in a machine learning model. So we're going to delete that. And origin. The issue, if we can call it issue with origin, is that origin is categorical. Notice that the data type for origin is object. Okay, object. Okay, and what that means is that origin is qualitative. So we need to convert it. We need to convert origin from categorical or qualitative into numeric. The way of doing that, or one of the way of doing that, is by creating dummy variables from origin, okay? And that's fine, we can do that. But the thing is, I don't want to use dummy variables in this case because I guess I could use dummy variables in a polynomial regression analysis if I were considering interaction terms between predictors. But in this video, I don't want to consider interaction terms. So I don't want to consider the dummies in that sense. I could also consider dummy variables in a polynomial regression analysis if I was considering kind of different polynomial models for the different origins. So here the origins are American, Japanese, European. So if I was doing like a kind of one polynomial model for American cars, another polynomial model for European, like that, well, maybe I can consider the dummies. I don't want to do that. So that's why I don't want to have dummies here, okay? So that's why I'm gonna delete these two variables, okay? Origin and name. And I do that right here by using the drop function. And sure enough, let's go ahead and execute this code cell. And once we take a look at the auto data frame, they are gone. Okay, so we don't have those columns anymore. Cool. Before we actually apply polynomial regression, let me remind you of something. I want to remind you of the usual steps that you should follow when you are training a machine learning solution, okay? And those are the steps we're gonna follow in this video, okay? I'm going to open a link to a chart provided in the Scikit-Learn documentation, okay? And I really like this chart because it explains the steps very, very well. Okay, here it is. This is the chart from the Scikit-Learn documentation, and here are the steps. First, you have all the available data set, okay? And the first thing you're going to do is you're going to split the data set randomly into the training data and the test data, okay? Then you're going to use the training data and you're going to apply cross-validation on the training data. What for? To select among all the parameters, the best parameters. So let me repeat that. So you use the training data, you apply cross-validation. What for? To select among all the parameters, the best parameters, okay? Now, when you apply polynomial regression, what are the parameters, okay? So what are the parameters that you're selecting for when you apply polynomial regression? I guess it depends on your situation. So if for example, you know what predictor you are using to apply polynomial regression, then the parameter that you're choosing is the degree. So are you going to do a second degree polynomial, third degree polynomial? What is the degree, okay? But let's say you are in the situation where you don't know what predictor you want to use to apply polynomial regression. Well, in that case, the choice that you're making is among all the predictors, what is the one whose coefficients in a polynomial model yield the best predicted performance, okay? So the parameters that we are selecting for in a polynomial regression model really depends on, do we know what specific predictor we want to use or we don't? If we don't, we have to do a different selection, okay? All right, so whatever parameters you are selecting, you select the best parameters, and then what you do is you use those best parameters and you feed with the training data what they call the retrain model. The retrain model is the model obtained using the best parameters on the training data, okay? And then finally, what you do is you use that retrain model or final model. I like to call this the final model better. You use that final model to predict the test data and come up with the final evaluation, okay? All right, so let's go ahead and apply those steps, shall we? First, we're going to split the data set. Okay, that's the first step, split the data. Before splitting the data, I always like to create, it's kind of a best practice for me. I like to create a variable to store only the features, only the predictors, okay? That's the variable right here, only with the predictors. And I like to create a variable that stores the target, miles per gallon in this case. And then I use these variables to do the split. To do the split, I'm gonna use this function, train test split, and this function takes 4 arguments and it returns 4 pieces of output. So let's first take a look at the arguments. These are the arguments of that function. The first argument is just the variable storing the predictors. The second argument is the variable with the target. The third argument is the test size. So we're doing the classic 80-20% split. So 80% of the data devoted for training, 20% for testing. And that's what I'm specifying here. Testing data is 20%, 0.20. So that means training is 0.8, 80%, okay? And finally, this, the random state equals 1. What am I doing there? I'm setting the random seed equals to the integer 1. This allows us to control the randomness of the split. What do I mean by randomness of the split? Don't forget that when we split the data, a random subset of the observations become the training data and the rest become the test data. By controlling the randomness, I make sure that anyone using my notebook gets the same training data and the same test data. So I'm kind of controlling the reproducibility of my results, okay? All right, then these are the outputs of that function. I guess let's take a look at these four outputs to understand what they are, okay? Xtrain, Xtest, Ytrain, and Ytest. So Xtrain is just a data frame. Oh, I'm sorry, I never executed this code cell. So now we can take a look at Xtrain. Xtrain is just a data frame with 313 observations. So that's 80%. That's 80% of 392. So Xtrain is the data frame with the training observations, but only the predictors, okay? So in Xtrain, we only have the predictor columns, okay? Not the outcome, not miles per gallon, okay? Xtest would be, again, only the predictor columns and with the test data, so 79 observations. 79 is 20% of 392, okay? How about Ytrain? Well, Ytrain is the target, so miles per gallon, but for the training data, 313. And Ytest would be the target, so miles per gallon, for the test data, 79 observations, okay? Perfect. Let's actually go ahead now and apply polynomial regression. Now we are done with the first step, the splitting, okay? So when your goal is to apply polynomial regression, I think it is reasonable to start by fitting a second degree polynomial. And then later, you might fit a higher degree if you want to, okay, if you feel it's useful, okay? But in principle, I think it's a very reasonable idea to start with a second degree polynomial. That's why I'm going to start with a second degree polynomial, okay? Also remember that when we are applying polynomial regression, our goal is to fit a non-linear relationship that we think exists between the target and one predictor. Okay, don't forget that. So when you are applying polynomial regression, it's because you think there is a non-linear relationship happening between the target and the predictor. Okay, don't forget that. Okay, after that, after those reminders, so let's go ahead and try to tackle this problem. So let's try to find one or more features, maybe more than one, that seem like a reasonable, reasonable options for fitting a second degree polynomial. Now, what feature is a reasonable option for a second degree polynomial based on what I said about polynomial regression? Well, the one that exhibits or shows a nonlinear relationship with the target, right? So if polynomial regression is something that we do when we want to fit a nonlinear relationship, so a good candidate would be a predictor that shows a nonlinear relationship with the target, okay? And that's what I'm gonna look for right now. I'm gonna do a scatter plot, okay, to spot non-linear relationships, okay? And I'm gonna do a scatter plot between the target and each feature, okay? And again, what I'm gonna do with those scatter plot is to try to spot or detect non-linear relationships, okay? Okay, so I'm going to do that using a loop, this loop right here, and in that loop, I'm gonna loop through all the columns in Xtrain, and for each column, that is for each predictor, I'm going to create a scatter plot, but I'm gonna also fit a linear regression. So because you know in the scatter plot, I want to show the linear regression line and the polynomial of second degree. I want to show both models, okay? So the scatter plot and both models, okay? Let's go ahead and take a look at these results, okay? So execute that code cell, and you're going to see a scatter plot. Let me scroll down. You're gonna see a scatter plot for each feature and the target. So miles per gallon on cylinders, miles per gallon on displacement, miles per gallon on horsepower, okay? Now, what am I looking for in these scatter plots? Two things, guys, two things. I'm trying to see, I'm trying to detect nonlinear relationships, okay? And also I want to see cases where the polynomial model, the quadratic model, okay, the dotted red line, give us a much better fit than the linear model, okay? So I'm looking for two things, a nonlinear relationship and then clear evidence that the quadratic model is better than the linear one, okay? Okay, let's go. The first one, mass per gallon on cylinders. Is there a nonlinear relationship? I think it is. Maybe not super clear, but I think it is. So I think the cloud of points follow a somewhat parabolic shape, like a parabola opening downward. Okay, so this a kind of nonlinear relationship in that chart. Not super clear, but it's there. How about the second question? So is the quadratic model much better than the linear one? I don't think so. They are both very similar regarding their feet. Okay. So maybe cylinders is not a good option for a second degree polynomial. Miles per gallon and displacement. Is there a nonlinear relationship evident, or is a nonlinear relationship evident in that case? I think it is, guys. So the data points, right? Look at the data points. The data points follow a curvilinear trajectory, right? I think it's clear that the data points follow a kind of curvilinear relationship, okay? And also, is the quadratic model a better fit than the linear model? The linear model will be the blue line, and the quadratic model the red dotted line. I think it is. I think it's clear that the red curve fits better the data points than the straight line. Okay, so displacement is a good option for a second degree polynomial. When I look at horsepower, same thing. I can see a clear curvilinear trajectory. So the data points follow a clear curvilinear trajectory. The red curve gives me a better fit than the linear equation. So horsepower is a good candidate as well. Weight, same thing. I do see a curvilinear trajectory. I see the cloud of points following a curvilinear trajectory, and I see that the quadratic model is better than the linear one. And finally, acceleration. For acceleration, I do not see a clear nonlinear relationship. I don't see a curvilinear trajectory as clearly as I saw earlier. Okay, so I don't see the nonlinear relationship that clearly here, and I don't see the quadratic model giving us a better fit than the linear one. Okay, so my conclusion is that acceleration and cylinders, I'm not that sure that a polynomial regression of second degrees is a good option, but for displacement, it looks like a second degree is a good option. For horsepower, it looks like a second degree polynomial is a good option, and also for weight. Okay, and that's what I'm gonna do. I'm gonna fit actually a second degree polynomial between miles per gallon and weight, miles per gallon and horsepower, and miles per gallon and displacement, and I'm gonna select among those three what is the best option. Okay. All right, let's go ahead and do that. Let us feed, that's the next step, feed a second degree polynomial with the features chosen in the previous step, the three features that we chose. Okay. All right. Now we need to consider something to fit a second degree polynomial using Scikit-Learn. Before fitting, and this is what I wrote here for you guys. So before fitting a polynomial for a given feature, we need to transform the features to include its higher order terms. What do I mean by that? If we want to create a second degree polynomial with x1, we need to have both x1 and x1 squared, okay? So to do that transformation, to have both the linear term and the quadratic term, Scikit-Learn recommends us to use a pipeline. So Scikit-Learn recommend us to do that transformation using a pipeline, okay? And that's what I'm going to do. I'm going to use a pipeline to do that transformation. And to do a pipeline, I'm going to use the make pipeline function, okay? That function takes two arguments, and those two arguments actually kind of represents two different steps in the pipeline, okay? The first argument is this, polynomial features. Polynomial features. That's a function to define the degree of the polynomial. Okay, so that's the function that allows us to define the degree of the polynomial. And here we're saying that the degree of the polynomial that we want is 2, because that's what we're doing, fitting a second degree polynomial. That's kind of the first step in the pipeline. Get everything ready to fit a second degree polynomial. The second function, okay, defines the algorithm to use to fit the polynomial model. Okay, so that second function is the one that defines what algorithm you want to use to fit your second degree polynomial. Now, here we're saying that we want to use linear regression, the linear regression function. What we're saying here is the following, guys. We're saying that we want to get the coefficients of the polynomial model using least square regression, kind of ordinary least square regression. Remember that least square regression is the same algorithm that we use to fit a plain linear regression model, okay? And it seems confusing for many people, like, oh, so we use linear square regression to fit both a linear equation and a polynomial equation? And the answer is yes, okay? Now, the key to understand that seemingly confusing situation is to understand the difference between a linear relationship and a linear model. Now, I'm not going to discuss that difference in this video, but if you're interested in understanding like why we use linear square regression for both linear regression and polynomial regression, look for the difference between a linear relationship and a linear model, okay? Okay, so let me go ahead and execute this code cell to create the pipeline. And next, I create a list with the three features that I want to try in a second degree polynomial, okay? Displacement, horsepower, and weight. Good. Then this is just a data frame. Right now it's an empty data frame where I'm going to store the results of cross-validation, because I'm gonna apply now cross-validation first with displacement, then with horsepower, then with weight, and I want to see which one of these three features gives me the best second degree polynomial, okay? So to store the cross-validation results, I'm going to create a data frame with two columns, the predictor under consideration and the cross-validation MSE for that polynomial, okay? For the polynomial for that specific predictor, okay? Right now, again, this is just an empty data frame, but it will get filled after we run the following loop, okay? Now, this is a variable that defines how cross-validation will happen. Again, now we are with the training data, we're going to apply cross-validation to try three different polynomial regressions with three different predictors. And this variable defines how cross-validation will take place. So I'm using the k-fold function available in Scikit-Learn to say that I want to have 10 folds. Splits means how many folds you want to have. I want to have 10 folds. Yes, I want to shuffle. I want to randomize the data before doing the folds. And again, random state controls the randomness. So I want everyone using this notebook to get the same folds, okay? All right, perfect. Now, in the next code, let me execute this. In the next code cell, I do a loop where I apply cross-validation with each of the features and I fit a second degree polynomial with each of these three features to select which one is the best one, okay? Now, I apply cross-validation using this function. And first of all, notice that I'm doing a loop here, and I'm going through features to get poly. Features to get poly is just this list with these three predictors. Okay. Now I'm applying polynomial regression. I'm sorry, not polynomial regression. I'm applying cross-validation using this function, cross-val score. So that function takes a few arguments. So let's try to understand the arguments. The first one is this poly second degree pipeline. That's the pipeline that I defined earlier, okay? So what we're saying here is that, hey, we are applying cross-validation to evaluate the performance of the second degree polynomial because this pipeline, as you saw earlier, defines a second degree polynomial, okay? The next arguments are the predictor and the target. So this is the predictor that we're using, and this is the target, okay? The predictor is just that part right there. So here, what we're saying is that notice that we're using the loop variable I, okay? The loop variable I right here, xtrain I. We are using it to retrieve the column I want to use as predictor from xtrain, okay? So I want that loop variable to retrieve the specific column that I want from xtrain, okay? This next thing, values reshape -1, 1, that's just a mandatory thing that we need to do in Scikit-Learn whenever we are using only one predictor. So whenever you're feeding linear regression or polynomial regression with only one predictor, Scikit-Learn forces us to change that predictor into a two-dimensional array. Okay, so we cannot work with a one-dimensional array in Scikit-Learn. So to be able to do that, to be able to transform a one-dimensional array, one single predictor, into a two-dimensional array, we need to do that. Okay. Perfect. So this is, as I said, the target. Of course, the target is stored in white train. Scoring. What is scoring? Scoring is how do you want to evaluate the results of cross-validation? Okay. How do you want to evaluate the results of cross-validation? And here we're saying that we want to evaluate the results of cross-validation using the negative mean square error. Ideally, we want to evaluate cross-validation using mean square error, not negative mean square error. Unfortunately, Scikit-Learn does not allow us to store the mean square error, but that's okay. I'm gonna transform the negative mean square error into mean square error by multiplying by -1. Do you see that negative right there in front of the function? Well, that negative will turn negative mean square into mean square. Okay. This is the cross-validation setup variable that we define here to control how the cross-validation will take place. And I'm storing the results of cross-validation in that variable, okay? MSC score CB poly. That, when cross-validation finishes for each predictor, that variable will store the cross-validation MSC for each of the 10 cross-validation iterations. So that will be a list. This will be a list with 10 numbers, okay? The cross-validation MSC for each of the 10 iterations. So at that point, what I really need to do is I need to get the mean of these 10 results. Remember that the cross-validation result is the mean of the result obtained from each iteration. So that's what I do in the next step. I use that variable and I get the mean, okay? And this would be the final cross-validation result for the polynomial associated to each predictor, okay? Okay, and then finally, I just append the results to this data frame, which originally, as I said, is empty, okay? So here, right here, I'm kind of appending the results. Okay, so let's go ahead and execute that code cell. And now let's take a look at this data frame, which again, initially was empty, but now it contains the information that we need. There you have it. So the second degree polynomial based on displacement has a cross-validation MSC of 1846. The second degree polynomial based on horsepower has a cross-validation MSC of 18.89. And the second degree polynomial based on weight has a cross-validation MSC of 17.48. So obviously the lower or the lowest cross-validation MSC is the one for weight. Okay. And remember, we want the lower the better. Okay. Because for MSC, mean square error, what do we want? High or low? We want low. So we're looking for the lowest MSC, okay? So the lowest cross-validation MSC happens for weight. So that is the best choice, okay? So as I said here, the second degree polynomial with weight gives us the best cross-validation result, okay? Perfect, that's fine. That's excellent. Like right now, we know the cross-validation MSC for the second degree polynomial based on weight. But what is actually the polynomial model based on weight? You know what I mean? So what are the coefficients for the second degree polynomial based on weight? That's what I want to do right now. I want to get the coefficients for that second degree polynomial based on weight. And that's what I'm doing here. I'm using that same pipeline that I defined earlier, but I'm feeding a polynomial regression specifically with weight, okay? Specifically with weight, X train, weight. And I'm storing the results in that variable. And now from that variable, from poly second degree weight, okay, from that variable, poly second degree weight, I can retrieve the intercept and the coefficients, okay? Let's go ahead and do that. This is the intercept and these are the coefficients. So this is the coefficient for the linear term and this is the coefficient for the second degree term, okay? And I wrote down the equation for you, predicting miles per gallon, which is the target, intercept, then the coefficient for the linear terms times weight, and the coefficient for the second degree term times weight square, okay? So that is our model. That is the retrained model, okay? That's the final model that we have obtained, okay? That's the final polynomial model that we have obtained from the training data, okay? Cool. So what do we need to do now? Well, we need to use that final model, predict the test data, and come up with a final evaluation, okay? That's what I do next. I use that model, poly second degree weight, and I predict the test data, and I store the predictions in that variable. Y predict poly weight test. Those are the predictions given by that polynomial model. And now the final evaluation that I'm going to propose is simply the root mean square error. So in regression, the root mean square error is a a standard metric to evaluate the quality of a regression model. So I'm just going to use the root mean square error, okay? But it's the root mean square error computed on the test data, so it's actually the test RMSE. Okay, RMSE means root mean square error. Thankfully, there is a function in Scikit-Learn to compute the root mean square error right there. And you pass a variable with the actual values of miles per gallon, and that's the variable with the actual values of miles per gallon, and then this is the variable with the predicted values of miles per gallon given by the polynomial. Okay, and here it is. So the RMSE is 4.28. Okay, 4.28. The units of the RMSE are the same as the units of the target. The target variable is miles per gallon, so this would be 4.28 miles per gallon. Is that a low error or not? So at this point, we need to actually judge this error. It's an RMSE of 4.28 miles per gallon, low, for us to claim that the polynomial model is good. And this is tricky because it really all depends on the units of the target variable. You know, it depends on the range of values taken by the target. Okay, so the recommendation here is that instead of attempting to kind of in a vacuum to judge the value of the RMSE as low or not, what you should do is you should put the RMSE into context, okay? And one way of doing that is expressing the RMSE relative to a typical value. That's a smart thing to do. So express or represent the RMSE relative to a typical value of the target. And what is a typical value of the target? The mean, guys, the mean of the target. So the mean miles per gallon, okay? And guess what? That's precisely what the coefficient of variation does. The coefficient of variation computes the division between the RMSE and the mean of the target, okay? In this case, RMSE and the mean miles per gallon, okay? So let's go ahead and compute the RMSE. I'm sorry, the coefficient of variation, which, by the way, is a percentage, okay? You can represent it as a percentage if you want, okay? And the coefficient of variation puts our MSC into perspective, okay, into context. So that's the mean miles per gallon. And now we're ready to compute the coefficient of variation, test our MSC divided by miles per by the mean miles per gallon. That's the coefficient of variation as a proportion, and this is the coefficient of variation as a percentage, which is much better, okay? Well, 18.22. Again, we need to make a judgment. Is this coefficient of variation good enough? And by good, I mean low enough. For the coefficient of variation, again, we want as low as possible, okay? So ideally 0% or close to zero would be ideal, okay? I mean, 0% is not going to happen because 0% means that our MSC is zero, but, you know, as close to zero as possible. Okay, so what do we do here? Well, the thing is, like for the coefficient of variation, thankfully, there are kind of, let's say, well-established standards to evaluate the coefficient of variation. And this is the idea. If the coefficient of variation is less than 10%, that's an excellent model. That's a very good model. So the error for your model is very good. You can judge the error of your model as being very good, okay? Less than 10%. But if the coefficient of variation is at least, you know, like less than 20%, that's acceptable. So as long as the coefficient of variation is less than 20%, that's an acceptable model. The error associated to your model is acceptable, okay? Well, in this case, we're getting a coefficient of variation of 18.22. So it's not less than 10%, but it's less than 20%. So what we should claim is that the value of the RMSE is acceptable, okay? So So it's not still ideal, but it's acceptable. We want to do better, but at least it's acceptable, okay? Because it's less, but because the coefficient of variation is less than 20%, okay? So takeaway is always try to put the RMSE into context. And one way of doing that is by computing the coefficient of variation and then using the best practices that I said to interpret the coefficient of variation. Okay. Okay, guys. So now here we can do one more thing. Let's do one more thing, and that will be the last thing we're going to do, which is um, so far we have a second degree polynomial based on weight, but maybe a third degree polynomial based on weight might be better. Maybe a fourth degree polynomial based on weight might be better. You know what I mean? Maybe a higher degree polynomial is better, right? So let's find that out. Okay, would a higher degree polynomial be better? Would a higher degree be a better choice for a polynomial based on weight? So again, right now we have a second degree polynomial, but let's try a couple of more degrees and see if we get a better performance. Okay. Now this is the thing, guys. Let's say from prior experience applying polynomial regression, the suggestion is that, or the indication, right, from prior experience is that it's rare. Okay, let's say like that. It's rare to find a good polynomial with degree above 4. So that's why when you are applying polynomial regression, the recommendation is not to go above 4. So 4 or less. Okay, that's why here I'm trying only 3 degrees. So I'm comparing only 3 degrees, 2, which is our current degree, 3 and 4th, okay? Perfect. So I store these degrees in that list. And now what I'm gonna do is in a loop, I'm gonna go through this list and create a polynomial of second degree, compute the cross-validation MSE, then do a third degree polynomial and compute the cross-validation MSE, and then do a fourth degree polynomial and compute the cross-validation MSE, and then compare the results, okay? This is a data frame, df. That's a data frame where I'm going to store the cross-validation for the different degrees. Okay, cross-validation for the different degrees based on weight. Okay, again, initially that's an empty data frame, but it will be filled with data after the loop. And the loop is this. And as I said earlier, I'm looping through this list with the different degrees. Okay, and notice that again I'm applying the same thing, guys. Same thing. Same function to apply cross validation. The difference is right here. Well, I guess a couple of differences, but the first difference is here. Look that at each iteration, I'm trying a different. I guess I can add here degree. Okay, let me add that right there. So the degree will be given by the I variable in the loop. Okay, so I'm trying different degrees as I go through the loop. And another difference is that here we are using specifically weight, right? Before we were trying like weight, displacement, and horsepower. Here we are using weight. Okay, so we are fixing weight, specifically weight. Okay. Okay, so but it's the same loop as before with those two minor changes. Okay. Let's go ahead and execute that code cell. And now let's take a look at this data frame, guys, which is not empty anymore. Okay, it's not empty anymore. Okay. And there you have it. What's the conclusion? So a second degree polynomial based on weights, we already knew this, has a cross-validation MSE of 17.48. A third degree polynomial based on weight gives us a cross-validation MSE of 17.51. And a fourth degree polynomial based on weight gives us a cross-validation MSE of 17.51. So what is happening? So third and fourth degree give us higher cross-validation MSE. That's not a good sign. Remember, we're looking for the lower MSE, the better, right? Like the lowest possible MSE, right? So what we're seeing here is that if we increase the degree, the MSE actually increases. That's a bad sign. That's a bad sign. That means that actually the best option is a second degree polynomial. And that was actually my conclusion. The best option is to use a second degree polynomial for weights because that's the polynomial that gives us the lowest cross-validation MSE, okay? All right, guys. So that's all for this video. I hope you enjoyed, and I hope you learned how to apply polynomial regression in Scikit-Learn. And I will see you in another video. Bye, guys.